Welcome to Month 6, the final session of the DevOps Engineer track. In the last 5 months, you built a continuous integration pipeline, containerized an application with Docker, deployed it to Kubernetes with Helm, provisioned that cluster with OpenTofu, and added full observability with Prometheus, Grafana, and Loki. Tonight you wire all of it together into a production-grade delivery system. This is the Capstone. The 5 learning objectives reflect what you will be able to demonstrate by the end. Authoring a complete end-to-end pipeline from lint to progressive deploy, implementing automated Canary analysis with real Prometheus metrics, generating SBOMs and signing images with Cosign, running a Capstone demo that survives a deliberately injected failure, and treating your pipeline as curviewed, versioned, and tested like any other software. The Capstone pipeline has 2 lanes, a PR lane and a main lane. Understanding the separation between them is the central architectural decision of this session. The PR lane runs on every pull request, lint, then unit test, then image build, then SBOM generation. The PR lane does not sign images. It does not scan for vulnerabilities at full depth. It does not deploy. The PR lane is optimized for developer feedback speed. It should complete in under 3 minutes on a warm catch. The main lane runs on merge to the main branch, Trivi vulnerability scan, Cosign signature, push to harbor with the git commit SHA as the image tag, trigger Argo Rollouts Canary deployment, then wait for the rollout to complete. The pipeline does not report success until Argo Rollouts reports the Canary as either promoted or aborted. The audit chain flows from right to left through that diagram. Every pod running in your cluster can be traced back. The pod shows you the image digest. The digest links to a Cosign transparency log entry. The log entry contains the commit SHA. The commit SHA points to the pull request and the author. That chain is a compliance requirement in regulated industries and a debugging superpower everywhere else. A stage gate is an explicit decision point where the pipeline stops and evaluates before continuing. There are 5 in this capstone, and each one is non-negotiable. Gate 1 is the coverage gate. The unit test job fails if code coverage drops below 70%. This threshold is not arbitrary. It represents the team's agreed confidence level. A pull request that reduces coverage below that threshold does not merge automatically. Gate 2 is the vulnerability gate. Trivi fails the build on any unsuppressed HEH or critical CVE. Unsuppressed is the key word. You maintain an allow list file of accepted vulnerabilities, each with a justification and an expiry date. Every accepted risk is documented, not hidden. Gate 3 is the signature gate. Cosign keyless signing creates a transparency log entry. If someone pushes an unsigned image by bypassing the pipeline entirely, admission controllers can reject it at deploy time. The signing gate is the enforcement mechanism for the entire build chain. Gate 4 is the analysis gate. The analysis template queries live Prometheus data during the Canary. If the 5x error rate or P95 latency exceed their thresholds, the analysis run fails and triggers automated rollback. No human decision required. Gate 5 is the rollout health gate. The pipeline waits for the rollout to complete. If the rollout aborts due to a failed analysis, the pipeline job exits non-zero. The engineer who merged the pull request sees a failed run. The on-call receives an alert from Alert Manager. The 5 artifacts, image, SBOM, signature, deployment manifest, and release notes, are produced automatically at each gate. If any of them require a human to produce manually, they will be skipped when someone is under pressure. Progressive delivery is the practice of shifting traffic gradually from an old version to a new one, with automated evaluation at each step. There are 3 main strategies, and they solve different problems. Canary deployment sends a small percentage of real traffic to the new version, typically 10%, then 25, then 50, then 100. At each step, an analysis template evaluates live metrics. If analysis passes, the rollout promotes. If it fails, traffic reverts to the stable version automatically. Canary works best when your Prometheus metrics are reliable enough to act on, and you want real traffic to validate the change. Blue-green deployment runs the full new version in parallel with the old one, then flips all traffic at once. There is no partial rollout, it is a binary switch. The benefit is zero in-flight request impact at the switch point. The cost is double the compute during deployment. Blue-green is the right choice when a schema migration makes the old and new versions mutually incompatible, so you cannot tolerate mixed version traffic. Feature flags decouple deployment from release. You deploy the code to 100% of pods, but hide the feature behind a flag that only a subset of users see. Rollback means flipping the flag, not redeploying. The trade-off is complexity. Dead code paths accumulate if flags are not cleaned up after the feature is fully launched. The most common mistake is treating a standard Kubernetes rolling deployment with kubectl rollout undo as progressive delivery. That is a slow rollout with manual human intervention if something goes wrong. True progressive delivery has automated analysis. The system decides, not a person watching a dashboard at 2 a.m. Argo Rollouts is a Kubernetes controller that replaces the standard deployment rollout algorithm with a programmable one. You install it as a custom resource definition, then convert your existing deployment YAML to a rollout YAML. The pod specification is identical. The spec templates section does not change. Only the strategy block is replaced. The component chain works like this. The rollout controller watches rollout resources and creates replica sets, exactly as the deployment controller does, but it exposes a steps array that defines the rollout progression. Two services point to different replica sets. The Canary service points to the new pods, and the stable service points to the old ones. Nginx ingress splits traffic between them by adjusting annotation weights, which Argo Rollouts updates automatically as the Canary progresses. The Canary steps shown here are exactly what you will deploy in the hands-on. Set weight to 10%, pause for 2 minutes. Set weight to 25%, pause for 5 minutes. Set weight to 50%, pause for 5 minutes. Set weight to 100%. The analysis template evaluation begins at step 2, starting step. 2 means the first 10% step is a soft landing. There is not enough traffic to get a meaningful signal that early, so analysis is deferred until 25%. Running kubectl Argo Rollouts get rollout catalog. Watched during a deployment shows you the live progression, the percentage, the current step, the analysis status, and whether promotion or rollback is the expected outcome. The analysis template is the component that gives automated rollback its intelligence. Without it, you have a slow deployment with manual human pauses. With it, you have a system that can detect a misbehaving canary and restore traffic in under 90 seconds, without anyone being woken up. This template defines 2 metrics. The first queries the 5x error rate, the sum of HTTP 5x responses divided by total requests, computed over a 2-minute rate window. The success condition is that the result must be below 0.1, less than 1% errors. The second metric queries the P95 request latency, using the histogram quantile function. The success condition is below 500 milliseconds. The interval, 30s and count. 3 configuration means the template evaluates every 30 seconds and requires 3 consecutive failures before taking action. This prevents a single noisy data point from triggering a rollback on what might be a transient spike. The failure limit, 1 means after 1 failed evaluation period, the analysis run transitions to the failed state, which Argo Rollouts detects and converts into a rollback. The most important operational detail: the Prometheus query must actually return data during the Canary window. If the Canary service receives no traffic, the error rate is 0, which passes analysis. Before relying on this system in production, verify your analysis template by deliberately injecting failures. The failure case must be confirmed to work before the happy path is trusted. The PR pipeline has 4 stages: lint test, build, and SBOM generation. Each stage must complete before the next begins. Lint runs 4 tools in parallel: shell check on shell scripts, hadlint on the Docker file, yamlint on any YAML configuration files, and rough on Python code. The lint step catches entire classes of bugs before a single test is run: a Docker file that switches users without setting a working directory, a shell script that uses unquoted variables, a YAML file with inconsistent indentation. Every lint action should be pinned to a commit cache, not a version tag. Tags can be rewritten by a compromised upstream. Commit caches cannot. Test runs PyTest with a coverage gate. The cov fail under 70 flag makes the job exit non-zero if coverage drops below the threshold. A pull request that reduces coverage does not pass CI automatically. Build uses Docker buildix, with registry side catching against Harbor. The first build of the day is the cold run. All layers must be computed from scratch. Every subsequent PR build on the same base layer hits the catch and completes in under a minute for typical application changes. The critical output of the build stage is the image digest, passed to downstream jobs via a job output variable. Every downstream job references this digest directly, not a tag, not the word, latest. Digests are immutable. Tags are not. SBOM generation uses SIFT to produce a software bill of materials attached as a GitHub Actions artifact. The SBOM is not verified in the PR lane. Verification and signing happen only when code merges to main. The main pipeline runs after merge and inherits the image digest from the build stage. It performs 4 operations: scan, push, and deploy. Trivy scans the image by digest for high and critical CVEs. The scanner is configured to exit non-zero on any unfixed finding that is not in the allow list. If your base image contains a known vulnerability with no available fix, you add it to a triviignore file with a comment explaining the acceptance rationale and an expiry date. Every accepted risk is documented. The allow list grows slowly under review and shrinks as fixes are released. Cosign keyless signing uses an OIDC token issued to the GitHub Actions workflow. There is no private key to manage, rotate, or accidentally leak. The signing certificate is issued by Sigstore's Fulcio Certificate Authority, and the signature is recorded in Recur's public transparency log. Anyone can verify the signature, and the verification output contains the exact GitHub Actions workflow URL that performed the signing. This is supply chain security without the operational burden of key management. After push to Harbor with the git commit SHA as the image tag, the pipeline triggers an Argo rollout by running kubectl Argo Rollouts set image catalog with the full digest. Then it blocks on kubectl Argo Rollouts wait catalog, timeout 20m, and if the rollout completes successfully, the pipeline job exits 0 and the run is marked green. If the rollout aborts due to a failed analysis run, the wait command exits non-zero, the pipeline fails, and Alert Manager fires the deployment failed alert. 2 operational discipline points separate a pipeline that works in a demo from one that works reliably in production over months. Concurrency control. For pull request workflows, cancel in progress. True cancels the currently running workflow when a new commit is pushed to the same branch. If you push 2 commits in rapid succession, only the second pipeline runs. The first is obsolete and its runner time is reclaimed. For main branch workflows, the opposite is required. Cancel in progress. False with a shared concurrency group. Serializes deployments. If two merges happen in quick succession, the second deployment waits for the first to complete before starting. You never skip a deploy, and you never have two rollouts competing for the same cluster namespace. Seshe pinning. Every uses reference in a GitHub Actions workflow should resolve to a commit seshe, not a version tag like v4. Version tags can be rewritten by maintainers, intentionally in a release, or maliciously in a supply chain compromise. A tag-based reference is a dependency that can change without your knowledge between pipeline runs. Tools like Dependabot can automate SA pinning and send pull requests when new versions are released, so you get the security without the manual maintenance. The image digest propagation pattern closes a subtle security gap. If each pipeline stage independently resolves a tag to a digest, a concurrent push to the registry between stages could different stages to act on different underlying images. Pass the digest once as a job output from the build stage and reference it in every downstream stage. The digest is the single source of truth. Converting an existing catalog deployment to an Argo rollout requires 4 changes to your Kubernetes manifests. The first change is to the resource type itself. The app version changes from apps v1 to Argo Proj.io v-alpha1, and the kind changes from deployment to rollout. The spec template pod specification is completely unchanged. Every container, every volume, every environment variable stays exactly as it was. The second change is to the spec.strategy block. Replace the existing rolling update strategy with the Canary strategy block. This includes the 4 wait steps, 10, 25, 50, 100%, with pauses between them, the analysis template reference starting at step 2, and the names of the Canary and stable services. The third change is to create 2 new services. The stable service selects pods with the stable replica set label. The Canary service selects pods with the Canary replica set label. Argo Rollouts manages the label assignment automatically. The Nginx ingress wait annotation, also managed automatically, distributes traffic between these 2 services according to the current Canary step. The fourth step is to apply the analysis template. Verify that it references the correct Prometheus service address for your cluster. In a Kube Prometheus stack installation, the correct address is typically HTTP, Prometheus operated, monitoring, das VCT cluster local 9090. An incorrectly addressed Prometheus query returns no data, which evaluates as passing analysis, a silent configuration error that only reveals itself when you need it most. The inject failure scenario is the most important part of this capstone. A delivery system that has never been tested under failure conditions is not a delivery system. It is a delivery hope. The pattern uses a feature flag implemented as a Python dependency. The Canary-only flag function checks an HTTP header. When the header is present, the endpoint returns HTTP 500. When the header is absent, it returns the normal response. In the Canary replica set, an environment variable activates the flag. In the stable replica set, the variable is absent. Canary traffic carries the header. Stable traffic does not. When a load generator or synthetic smoke test sends requests with the X-Canary true header, 100% of Canary traffic returns 500. The stable pods are completely unaffected. From the perspective of real users, nothing has changed yet. The analysis template sees the error rate on the Canary job spike above the 1% threshold. After 3 consecutive 30-second evaluation intervals, 90 seconds total, the analysis run transitions to failed. Argo Rollouts immediately sets the rollout phase to aborted and patches the Nginx ingress wait annotation back to 0% Canary. The Canary service stops receiving traffic. the stable service takes 100%. Within the next Nginx reload cycle, typically under 2 seconds, all traffic is on the stable version. This is the capability that matters, not the happy path. Any deployment tool can do the happy path. The distinguishing capability is automated, data-driven rollback without human intervention. Let's trace the automated rollback event sequence from the first bad metric to full traffic restoration. At time 0, the Canary deployment starts. 10% of traffic now reaches the new pods. The analysis run begins its first evaluation interval. At 30 seconds, Prometheus completes its first scrape within the 2-minute rate window. The error rate is already elevated. The injected bug is deterministic. The analysis run records 1 failure. At 60 seconds, the second evaluation interval completes. Still failing. Second failure recorded. At 90 seconds, the third evaluation completes. The failure limit, 1 threshold, is now exceeded. The analysis run transitions to the failed state. Within 1 second, Argo Rollouts detects the failed analysis run and sets the rollout phase to aborted. It patches the Nginx ingress wait annotation to 0% Canary. Nginx picks up the annotation change within its next reload cycle and updates the upstream waits. 100% of traffic is now on the stable service. The Canary pods are still running but receive no requests. Simultaneously, the pipeline's wait for rollout command detects the aborted phase and exits non-zero. GitHub Actions marks the workflow run as failed. Alert Manager fires the deployment failed alert. The engineer who merged the pull request sees a red run in their notification feed. The entire sequence, from the first bad metric reading to full traffic restoration, occurred automatically in under 2 minutes without any human action. The Capstone quality bar is defined by 5 properties. Understanding these properties and what specifically makes them true is the difference between a pipeline that works and one you can trust. Reproducible means the same. Git commit always produces the same image digest. This requires pinned dependencies, content addressable build layers, no timestamp in the image metadata, and no random seed in the build process. If 2 separate pipeline runs on the same commit produce different digests, something in the build is non-deterministic, and the reproducibility property is violated. Traceable means every running pod can be linked back to its origin. From the pod image digest, you retrieve the Cosign transparency log entry, which contains the commit SHA and the workflow URL. From the commit SHA, you find the pull request, the reviewer who approved it, and the test results from that run. The full chain takes under 2 minutes to traverse. Reversible means restoration to the previous state requires 1 command. The previous stable replica set is still running. Argo Rollouts does not delete it until the rollout is fully promoted. Rolling back is instant, not a redeploy. The time to restore is measured in seconds, not minutes. Reviewable means every deployment affecting artifact exists in Git. The pipeline YAML, the rollout manifest, the analysis template, the Helm values, the Terraform for the cluster infrastructure. Nothing exists only in a cloud console or a person's memory. Observable means every pipeline run and every rollout emits metrics. Argo Rollouts ships a metrics endpoint that Prometheus stack scrapes automatically. The rollout phase metric tells you the current state of every rollout in the cluster. A Grafana dashboard can show you the rollout history alongside the application's 4 golden signals. After building the pipeline, the next step is to review it the way a senior engineer or a security reviewer would. These are the questions that reveal whether a pipeline is production-ready or just demo-ready. Where could a secret leak? The most common path is a shell command that interpolates a secret into a string that gets logged. Docker login $p password echoed echoes the registry URL to stout. If your logging captures stout, the password may be captured. The correct form is echo power docker login, password stin. Any place where a secret is interpolated into a string that might be printed is a potential leak. Where could a malicious pull request exfiltrate from? On GitHub Actions, pull requests from forks run in a restricted context with no access to repository secrets. But pull requests from branches within the same repository have full secret access. A contributor with write access can open a PR with a workflow step that exfiltrates secrets from the environment. Mitigation is environment-scoped secrets with required reviewers on the production environment, so no push to main can happen without human approval. Where is the slowest stage? Typically the Trivy vulnerability scan on a cold database download. Catch the Trivy database as a registry artifact or use the Catch There option mounted from a persistent volume. Warm scans should complete in under 30 seconds. What does the pipeline cost per merge? Estimate the runner minutes per stage, multiply by the GitHub Actions or self-hosted runner cost. Add Harbor storage for the image. A typical run costs between 5 and 20 cents, depending on image size and test duration. At 50 merges per day, that is between $2 and $10 per day, a reasonable cost for the confidence provided. This capstone integrates every skill from months 1 through 5. Seeing where each month's work appears in the final system is the retrospective that makes the track coherent. Month 1's contribution is the pipeline shape itself. The lint, test, build stage progression was established in month 1. What changed is the build output. Instead of a local Docker image, it produces an image digest and SBOM. The pipeline as code discipline from month 1 is applied here at higher intensity and with higher stakes. Month 2's contribution is the hardened container image. The multi-stage Docker file, the non-root user, the minimal base image, that is the image Trivy now scans. If you cut corners in month 2, the vulnerability gate fails here. Month 3's contribution is the Kubernetes workloads. The rollout is a superset of the deployment. The Helm chart skills, the config map and secret management, the resource limits and health probes, all of that carries forward unchanged. Month 4's contribution is the cluster infrastructure. The kind cluster running tonight was provisioned with the OpenTofu module from month 4. Adding Argo Rollouts to the cluster is a Helm release in that module, a controlled infrastructure change, not a manual kubectl apply. Month 5's contribution is the observability stack. The analysis template queries the same Prometheus installation you configured in month 5. The SLO error budget thresholds from month 5 are the basis for the analysis template success conditions. The runbooks you wrote in month 5 are the first documents an on-call engineer reaches for when a rollback fires. What is still missing before this system is genuinely production-ready. Pre-production smoke tests, contract tests between services, multi-region rollout with geographic failover, and compliance attestations SLSA level 2 or higher. Those belong to the senior DevOps engineer and architect tracks. The Capstone Challenge has 4 deliverables, each worth 25 points, for a total of 100 points. Passing score is 75 points. Deliverable 1 is the pipeline as code file. The evaluator will check that the PR lane and main lane are cleanly separated, that the image digest is propagated as a job output. That caching is demonstrably effective by comparing warm and cold timing, that the file is under 400 lines and readable by someone unfamiliar with the project, and that every action and base image is pinned by a digest. Deliverable 2 is the Argo Rollouts manifests, the rollout resource, the analysis template, and the Canary and stable services. The evaluator will trigger a deliberate failure and verify that automated rollback completes within 90 seconds of the first analysis failure, without any manual intervention. Deliverable 3 is the Capstone demo transcript. It must include the full event timeline from PR open to live deploy, the inject failure scenario with the rollback firing, and the audit trail trace from pod to author. The non-functional timing targets: under 8 minutes for a cold pipeline run, under 15 minutes for a rollout, must be evidenced with real timestamps, not estimates. Deliverable 4 is the retrospective. The security review section earns full marks only when it names specific leak paths from your actual pipeline, not generic risks from a checklist. The cost and speed analysis earns full marks only when it includes real numbers from your own runs. You have completed the DevOps engineer track. In 6 months, you built a CI pipeline from scratch, containerized and hardened a service with Docker, deployed it to Kubernetes with Helm and GitOps discipline, provisioned the infrastructure with OpenTofu, added full observability with the Prometheus stack, and now wired all of it together into a delivery system with progressive deployment and automated rollback. That is a real engineering capability, not a tutorial walkthrough, a system you built yourself that runs real software, that can recover from a deliberately injected failure in under 2 minutes without human intervention. The Senior DevOps Engineer track takes 3 significant steps further. GitOps multi-cluster with Fleet or Argo CD scales this pattern to multiple environments and multiple clusters without manual kubectl commands. Supply Chain Security, SLSA Level 3, adds provenance attestations and policy as code enforcement that meet regulated industry requirements. Internal Developer Platform Self-Service gives product teams the ability to provision environments, deploy services, and manage their own observability without a ticket to the platform team. The single most valuable habit you can take back to your current work today is this: treat your pipeline YAML like application code. Review it before merging. Test the failure paths deliberately. Keep it under 400 lines. Remove what you do not need. If you do nothing else from this session, that one habit will make you a more reliable engineer starting tomorrow. Congratulations on completing the track.